Okay, number 20. This is a great review question of lots of different things we've done, including a Riemann sum here in part A, a little bit of interpreting the derivative in part B, and working with the approximation of the derivative using a table, the average rate of change, or AROC, part C, and then something new in part D, which we'll talk about when we get there. So test plane flies in a straight line with a positive velocity v of t in miles per minute at time t minutes, where v is a differentiable function of t. Selected values of v of t for 0 to 40 are shown in the table above. Use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate the integral from 0 to 40 of v of t dt. Show the computations that lead to your answer using correct units. Explain the meaning. So there's a lot going on here. One is to get the answer using the midpoint sum, and then to explain the meaning of the integral. So first of all, 4 intervals of equal lengths, and we're using the midpoint. So that means my first interval is going to be 0 to 10, and the midpoint is going to be 5. The next interval is 10 to 20, and the midpoint would be 15. 20 to 30, the midpoint's 25, and then 30 to 40, the midpoint is going to be 15. So the approximation is going to be, I'm going to scroll down here. I should be able to get it in here. The integral from 0 to 40 of v of t dt is going to be, well, the width of this interval is 10, from 0 to 10 is 10, times the height of this interval, we use the midpoint, that's 9.2, plus the next interval has a width of 10, as does the other intervals. 10 times the height of that interval, which would be 7, plus 10 times the height of the next one, which is 2.4, plus 10 times the height of the next one, which is 4.3. Add that all up, we get 229. The interpretation is that 229 is so this is the total distance, the accumulated distance flown by the plane in 40 minutes. All right, let's take a look at part B. Based on the values in the table, what is the smallest number of instances at which the acceleration, now again, as soon as I say acceleration, we're talking v prime, when the acceleration could be 0 on the open interval. So we're looking at v by our table and asking what happens when v prime, or what's the smallest number of instances when v prime is 0. Well, again, v prime is 0 when v prime changes from negative to positive or positive to negative. So v prime is 0 when v prime changes from positive to negative or negative to positive. Now, when does that happen? That happens when v changes from increasing to decreasing or decreasing to increasing. So we now need to go back to our table and say, where does it change? What's the fewest number of changes from increasing to decreasing or decreasing to increasing could there be? So let's just take a look up here. So first of all, note the answer technically could be infinitely many, because just the fact that I go from 7 to 9.2 over the first 5 minutes does not mean the graph doesn't go way up and then come back down and way up again and come back down and way up and come back down and finally settle at 9.2. So it could do this infinitely many times, but we want to assume the nicest graph looking at the fewest number of changes. So we are increasing 7, 9.2, 9.5, and then all of a sudden, here somewhere, there has to be a change. Now, it could happen on the other side. It could go up to 10 and then start decreasing down from there. But again, we're going for the easiest possible situation. So that would be one change where we start decreasing now. Goes 7 to 4.5 to 2.4. Then it stays the same. So that's a 0 change. So right there. And then it's increasing again all the way the rest of the table. So the answer is there are 2. That's the fewest number of times where the acceleration could be 0. So v changes from increasing to decreasing, which happens at least 2 times. All right. Use the data in the table above to approximate the value. So v prime of 12.5 is approximately. All right, so let's take a look. So 12.5 is sitting right in here between 10 and 15. So we're going to use these values right here, 10 and 15. And so we're going to go ahead and just compute the average rate of change. That is, I'm going to do v of 15 minus v of 10 over 15 minus 10. So v of 15 is 7, v of 10 is 9.5 over 5. 7 minus 9.5 is negative 2.5 over 5 is negative 1/2. All right, and then D, the function f defined by f of t is used to model the velocity of the plane in miles per minute for 0 to 40. According to this model, what is the value of 0 to 40? Now, we're going to eventually get to the point where we could calculate this. We technically could using some substitution. We'd have a couple of different u values here, one where u is t over 10, and so we'd need a 1/10 somewhere. The other thing we'd need is a 7/40ths and so on and so forth. So really complicated. So I'm going to show you how to use the TI calculator to calculate this integral from 0 to 40 of f of t. So let me switch over to that. So the first thing is in my y equals is I punched in the function here. So 6 plus the cosine of x over 10. Again, the function uses x, so I need to make sure I switch from t to x here. Plus 3 sine of 7x over 40. So I'm going to go back and, sorry, second quit. And to calculate the integral, we go to math, and we go down here to 9. So you can scroll down or just hit the number 9, it doesn't matter. So here we have our integral all set up. We're going from the integral from 0 to 40 of, I want that function. So remember, to do the function, if you've typed it in, we go vars, y vars, function y1. And then the variable we're using here, if it was x, or we could be using t or some other letter, so we're going to hit dx. So when I hit enter, I get my answer of 287.2887. So we go back to our page here, and I write 287, rounding it to 3 decimal places, 289. Indicate units of measure. This is going to be miles. That completes the FRQ for the study guide. If you have any questions, don't hesitate to reach out.